Okay, so geodesic equation. That was really the main point of this week. The geodesic equation is an equation, and it tells you how things move in a curved space-time. And if you've read the book about this, the book also spends time saying that there is something called the geodesic equation. They also say where it comes from in principle. Right? If you remember for Tuesday, the geodesic equation is the equation that tells you how you get from point A to point B in a curved space-time such that the proper time along that path is the smallest. Mm-hmm. Now there's reasoning why you want the path of least proper time. The book doesn't address that for some reason. I like the book a lot, but that point they don't really make. They just say this is what nature does. And they call it the variational principle in some box in chapter 7, I think. They say, or 6. And they say, well, nature just always chooses a path of least proper time. And I think you should know a little bit more than that. Again, I'm very happy with the book, but this particular thing I don't understand why they don't explain. So I want to spend just a second more on the geodesic equation. Let's write it down first, and then let's do some exercises. Now, at some point people always ask, do I have to know this by heart? And the answer is no. You get this on your formula sheet, but of course at some point if you work long enough with any equation you will know it by heart. So,
one question?
Yes.
Because I was kind of missing in the lecture, how do you write this thing, like the gamma thing?
I'm going to, what it means?
Oh yeah.
Yeah, that's what I'm going to write down now.
Why? Oh, never mind.
Okay, fine.
No, I was going to ask why it's a full derivative, not a partial derivative, the first term.
This one?
Yeah.
Yes.
Why is it not a partial derivative?
Oh, that's very simple, because our coordinates will only depend on tau. So it doesn't matter which one.
Okay.
So that's exactly what the thing does. It will, this equation will tell you how a particular coordinate of a moving thing in space-time, how it will depend on tau.
Mm.
They will not depend on each other. Right? They're
True.
So that means the partial derivative is the full derivative. There we go. I had to collect my thoughts there for a moment. This is wrong, by the way. This is u, alpha, u, d, u. We will also discuss today why the thing looks the way that it does. But let's spend a little bit more time understanding where it comes from. So this is the path of least proper time. And again, you could say, well, that's a separate rule of physics. Apparently this is a rule that is true in general relativity, but let's spend a little bit more time on it. Do you remember what argument I gave during the main lecture? Why in a curved space-time nature chooses a path of least proper time?
The physical argument?
Yes.
No. I just remember the Euler-Lagrange equation.
Okay, the Euler-Lagrange equation just tells you if you have an integral and you want to make sure that the outcome is the smallest or the biggest, then you have to solve that equation. Sure. Yeah. But that's one step after we've concluded that it should be the smallest number. And that is my question now. Why does nature choose the path of least proper time?
Is it because it's the path of less distance and of less energy as well?
Well, if you mean distance as in the amount of meters, no, that's not necessarily the case. Proper time is a combination of dt and the axis, yes. So you can, I'm sure you can find some combination that the distance might not be minimal, but the amount of time compensates for this.
Okay.
I don't know if that's what you're looking for, but I remember that we said also that it was the straightest path as well.
Yes. And we were going to use that argument, but we need a little bit more. It had to do with zooming in. You have a curved space-time, you zoom in.
Oh, Minkowski space-time.
Yes.
In Minkowski space-time you have straight paths.
Yes, by definition, by the way, right? I mean, if you recall, in inertia frame, where the Minkowski metric holds, is by definition one, where things go in a straight line with constant velocity.
Why do things go in a straight line in flat space?
Yeah, I'm not sure I have a real answer to that. I can give you a circular reason argument, as in that if you define a coordinate system which things go in a straight line with constant velocity if no forces are acting on them, then obviously in such an inertial frame things will go with in a straight line with constant velocity. But if your question is why do things have inertia, why do things tend, why do things want to go in a constant line with a straight line with constant velocity, I do not have an answer.
Yeah, okay.
So apparently this is the nature of things. That is, I hate answering questions like this, but at some point in your physics you have to take a premise, right? If you go back to, I don't know, 2,000 years ago, Aristotle, like 400 years before Christ, his views on things were that the nature of things is that they always want to come to rest.
Mm-hmm.
And where do we want to come to rest? Well, at the center of the universe where there happens to be the Earth. This is his explanation for what gravity is and why things stop rolling if you have to give them, if you gave them a kick at some point. And then other people later on, 2,000 years later, it was 1500s or so, Galileo, Newton, then they realized, no, wait a minute, the rule's actually the opposite. Things don't want to get to rest, they want to keep on moving. And that probably, of course, as you know, is called inertia. But if you would ask me, why do things have inertia, I don't have an immediate answer. I have sort of an answer, but it's more philosophical. That is that if they do want to get to rest at some point, if they don't want to keep on moving with constant velocity, and that means that they will at some point get to rest, yes? But will get to rest with respect to what coordinate system? Because I can define all kinds of coordinate systems that are moving in this way, in that way, accelerating, etc. Which of all these coordinate systems is the one with respect to which an object wants to get to rest?
Yeah.
And this is sort of a philosophical argument. It sort of feels more natural to say, you know what? Maybe there isn't one preferred coordinate system with respect to which things define their motion.
Inertia doesn't favor any frame.
Exactly. So a sort of philosophical argument why things have inertia is saying, well, nature doesn't favor one particular coordinate system over the other. That I think is an equivalent statement.
Yeah.
That's not a full answer, but to me that does feel more natural. I think you have more explaining to do if you say, of all possible coordinate systems, it's this one that you have to favor, than that you have to explain that all coordinate systems are equal in that sense.
Yeah.
So it's not a full answer,
It
but I
makes
don't
sense.
think people can give a real
Yeah,
full
we
answer.
don't know. Yeah.
But to me it does feel more natural, and not just out of habit, it does feel more natural that if you find a rule of physics, that it isn't restricted to one particular coordinate frame. And you should be able to apply to many coordinate frames, and under that assumption, you cannot have a system where things want to get to rest. So you only have one option left, and it's that to keep on cruising. But it's not. I mean, if you ask me your first principle argument, I don't have one. But suppose that they do, yes. So we have our coordinate system in which things go with a constant velocity, in a straight line. Well, we call these inertial frames by definition. Right? We define an inertial frame or a Minkowski frame in space-time setting as coordinate systems in which things go with a constant velocity in a straight line. Well, you know that if you zoom in enough in a curved space-time, it will look approximately Minkowskian. And approximately Minkowski means that for at least a short amount of time, as long as your assumption of it being sort of Minkowskian holds, the thing will move in a straight line with constant velocity. Or, that's an equivalent statement, in that very small amount of time it will take the path of the least time between 2 points.
So you could integrate those infinitesimally small
Yes.
velocity vectors that are straight lines.
Yes,
And
exactly.
then get the entire geodesic.
Exactly,
Yeah.
that's what you do. If you have a curved space-time, here's our famous example, the sphere, and you want to get from point here to point there, then, well, let's make it more easy to draw. Along this part is the circumference of the full sphere. Well, certainly this is not a Minkowski space-time. The rules of Euclidean physics do not hold here. We've explicitly checked this last week when we were drawing circles on this and saw that 2 pi doesn't hold and these sorts of things. But certainly if you look at a very small patch, it's sort of Euclidean-ish, right? In fact, we also checked that last week, that when we drew a circle on a big sphere, we saw that if you made that circle's radius very, very small compared to the big circle's radius, then all of a sudden you do get your a ratio of 2 pi over the circumference of the small sphere and its radius. Right? Do you remember that we did that last week? So all of this is just saying if you zoom in enough on any curved space or space-time, it will look approximately Minkowskian, but only for a small amount of time. But in that small amount of Minkowski, it will move in a straight line. Which is another way of saying it will look for a path of least proper time. Now, then of course you're at this position, and look, at some point, if you make your patch too big, you will actually see the curvature here. Alright, so making the patch too big will not work, but what you can do is, take the next little patch, but note that the next little patch is a little bit skewed compared to the first patch. But in that next little patch, it will still be a straight line. And there you go. And so you build up your path along all kinds of little local Minkowski frames, Minkowski spacetime. In each you assume a straight line, or not assume, by definition it will be a straight line. And in each it will take the path of least proper time, so the total amount of time is just literally the sum of all the little pieces of proper time per local Minkowski assumption. And the book does mention that. They say that one of these patches is called a local Lorentz frame. That's how they call this in the book. Now, when I talk about these things, I always say Minkowski spacetime, or I say inertial frame. It's all just different phrasing of the exact same thing. So you might also abbreviate this to LLF. I think that's what the book does. Or you say local Minkowski frame. I guess you would abbreviate that by LMF. Or local inertial frame. I don't care what you call it, it's all the same thing. Local inertial frame, or LIF. But that's what you do. Now, how you do this in practice? Well, the proper time in a Minkowski spacetime, as you know from your special relativity, is the contraction of the Minkowski tensor. This thing here, in fact, so the amount is this. And yes, this is per each of these patches. If you want to have the full, then you just integrate over all the small patches. But now I'm making a small mistake, and I hope you see what. So this is the idea, yeah? You integrate over all the small patches. The smallest mistake that I'm making here is what we have encountered last week, actually. Last week, when we had a curved spacetime and we tried to describe it, what we first did is that we made things very small, so we could assume Pythagoras theorem, and we replaced the x, y, dz by whatever made the spacetime curve, and that resulted in the metric tensor, the thing that tells you the curvature. I haven't put the metric tensor in here yet. If I just leave this the Minkowski frame, then I'm assuming implicitly that all these patches are the same Minkowski frame. They're not. At any moment in time, there's a new Minkowski frame, and that.
So they'd have a different tensor?
Yeah, but they're all combining in the big metric tensor, right? That's exactly what we did last week. We started by saying in one little patch of a curved space, last week we only talked about spaces, there's Pythagoras theorem that gives you a metric tensor, but at any next point along the path, the metric tensor will change by a small amount, and that gives you your ultimate curvature. In fact, Rodrigo, that was your question. Last week you asked me how this thing resulted under the integration that it actually was curved, and I said that's because this thing itself will depend on the coordinates. So every time that you move to the next patch, this number will change a little bit accordingly.
That means also that if you were using the Minkowski metric,
yes,
and you would sum over, instead of the general or the G,
yes,
you would sum over eta,
yes,
you would get a flat
yes,
spacetime, right?
Yes. So this is certainly true at a small patch, but if you're going to integrate and take into account that every patch is a little bit skewed with respect to the previous one, then you need the general metric. That's exactly what the general metric tells you. That's how we used it, how we introduced it last week. So we have this requirement, and we have to minimize this number. In every patch, it's the smallest proper time, so that over the total curve through curved space-time, this number has to be minimized, this has to be minimized. Now the book then states without proof that this integration is minimized by this equation. They are right. In fact, they refer to their website. They say, if you want the derivation of this, look at website. No, it's fine. I mean, it's a long derivation if you want to go through this. But what the book also does is, the fact that this must be minimized, they claim is just a rule. Well, this is just happens what nature does. It's certainly true, but you can see that you can actually understand why it holds that way. At the moment that you are going to have a curved space-time, you're going to build up the little patches, and you know that in each patch, the proper time must be minimal, then this follows automatically. Notice that this argumentation holds by the fact that you can write a curved space-time as little patches of Minkowski space-time, otherwise this would not hold. The fact that you can write space-time as little patches of local inertial frames, that is guaranteed by the equivalence principle.
How is that?
Do you remember what the equivalence principle told you?
That if you're in an inertial frame, that's also equivalent to being in a gravitational field.
Yes, that's one formulation. The other one is that all objects follow the same path.
Yeah,
right?
yeah, that one.
That's enough. So all of this is just a mathematical rephrasing, or mathematical consequence, I should say rather, of the equivalence principle. The fact that this is true is just equivalence principle, but put into mathematics. Now the book does spend time on explaining the equivalence principle, explains these things. This is the missing step, so there you go. So, there's not a separate rule of physics, it really is just the fact that the equivalence principle exists means that this must be true. Now the question of course is, how do you minimize this? We know that it should be minimized. How do you minimize it? And now, fortunately, all of you, well, except for Ali, who did it in we did special relativity, but in a somewhat different phrasing. We discussed this during special relativity. Not in this particular context, but in mathematics we did discuss. So just to make a nice connection with special relativity, I'm going to rewrite the total amount of proper time in a very much the same way. Namely as follows. It's exactly the same expression, I just took a detail out. And going back to our special relativity course, we had situations where you would integrate some function over time, and that integration had to be minimal. Back then it was called the action.
Well, the principle of like extreme enhancing,
yes,
or something like
yes, that was that. Yes. Back then, I said that instead of using Newton's second law, you could also say, you know what? There is something that's called Lagrangian. You integrate it over time, and the outcome of that integral must be extremal, must be either minimum or maximum. Well, that's what we do here. Look, I have exactly the same mathematical structure. The context is slightly different, but the mathematical structure is the same. I have a function. By correspondence, might as well call it Lagrangian, just as we did in special relativity. Integrate it over time. Sure, it's not the normal time, it's proper time, but the mathematical structure is the same. And the question is how to choose things such that the outcome of this thing is minimal. And you might even remember that we had an equation for that during special relativity. We called that, so to minimize this, we derived, I'm not going to do it here in this course, but we derived in one of the tutorials on special relativity an equation that guarantees that this integral is minimized. If you don't know how that works, look up any somewhat advanced book in classical mechanics, or look at the tutorial recording of special relativity, it's still online. This is the rule. Take this thing, take its derivative with respect to one of your coordinates. Then set it equal to the time derivative of, again, this thing, its derivative with respect to the proper velocity, u alpha. Again, why this is true, see tutorial, special relativity, see book, advanced book on classical mechanics. But this is a mathematical fact. If you want this minimized, then you must make sure that this equation is obeyed, or no Lagrange. So I'm just borrowing the mathematics that we developed in special relativity. And now it's a beautiful thing. We have a Lagrangian, we have an L in our context now. It's this crappy square root with all the difficult stuff inside. You can put this in here, and if you work out all the derivatives, this is the equation you will get. Or Lagrange equation. That's where it comes from. Now, at the end of today's tutorial, we can discuss a little bit how you go through the derivation. It takes too long to do it here. But I can give some hints on how to work through this. Yeah, and I do advise that at some point, just as a practice in general relativity or Lagrange and in contractions, that you try to go through this derivation yourself, to go from here to there. It's extremely worthwhile education to have tried this. I will tell you, it will probably take you, it's not a 30-minute exercise, it'll probably take you a little bit longer.
Sunday afternoon.
Yes, and it just happened to know what the forecast is for this weekend. It's going to be raining on both Saturday and Sunday. So you have enough time to work on this. But this is where it comes from. So you see, all of this is just weak equivalence principle taken to its mathematical consequence. All right, beautiful. Now, let's apply this stuff. Okay, let's do an exercise. Let's start with a metric tensor. Write down the geodesic equation and calculate what kind of path nature apparently chooses for masses to follow in that space-time. So let's actually go through one of these exercises. Now before we do so, there's one very good question that somebody from the other group asked. He asked, now what if you're going to look at something that moves with the speed of light? Very good question. Because he said then the proper time of something that moves with the speed of light is 0. That is correct. Time dilation is infinite for photons or gravitational waves or massless objects. And then he said, well, that means that the tau is something that you cannot work with, right? What you will end up with, hopefully, is the 4 coordinates of your motion as functions of tau, but tau is completely ill-defined for something that moves with the speed of light, because tau is only 0 for that thing. So he said, what do you do if you want to describe something that moves with the speed of light? Can you do this by this equation? It's a good question, right? Now, let me say that that person, he deserves the credit, was Felix, he is completely right. That's a very good question. This equation, the geodesic equation, cannot be used for particles that move with the speed of light for exactly the reason he raised, for a suggestion that he raised. But you know that particles that move with the speed of light have a particular property. There's only one type of particle that can move with the speed of light. You might remember from special relativity. Statement, somebody?
Massless.
Massless, exactly. So that means the geodesic equation, as it is here, can only be applied for massive particles. Massless, you have to do something else.
So even ones that are close to the speed of light but
Yes.
have a mass,
Yes.
they still follow the geodesic.
Yes. So you don't have to worry that the geodesic equation becomes crappier and crappier as mass decreases. It works all the way until close to 0, except for 0 itself. It's really a discrete jump from very much close to 0 to exactly 0. So it's completely accurate as long as it's not identically 0, the mass. Okay, now how to do that in case of massless particles? I gave a short answer to the other people, and I'm not going to repeat it here. It is interesting, it is important, but I tend to go off on tangents.
Can you use it for neutrinos?
Yes.
But we're not sure whether they have mass.
No.
Oh,
They have mass because they know of the mass differences between neutrinos. They don't know what the masses a piece are. They are of electron volt value or something
Okay,
like
but
that.
they're close to 0, but you can
Yes.
still use it.
Yes.
Not even a statement?
Short statement.
You're tempting him.
Shortest statement I can try. As if I'm talking on TV now. Everything has to be one sentence, okay? Mathematically, you can say, you know what, I can take my tau and I can just add a number to it. Agreed?
Mm-hmm.
Then you can make a new variable that is some combination of tau. That itself, the new variable, will not be 0 anymore at any moment in time. Or I shouldn't say moment in time, moment in its own progression. So the fact that you cannot use tau simply means that the solution you will get, you cannot write as a function of the photon's proper time. But you can still define some other parameter that describes its path. You're just not allowed to associate that value of that parameter to the photon's time. And that's just a mathematical rewriting of tau. Now that thing, the new parameter, they call it lambda, it's called an affine parameter. It's sort of like time, where time is actually 0. Now if that sounds strange to you, listen, if I throw something here and I want to describe this Newtonian gravity, I want to describe it, I tend to do it as a function of time, agreed? I don't have to. I can also describe this thing's flying motion, its y, as a function of its x. No time in there. Mathematical description holds just fine. In fact, I can introduce some new parameter, lambda, that describes how its x and y, we would call it parameterization in mathematics.
Something they did in the video.
It just means
Yeah,
that
yeah.
the parameter that you use
Exactly.
doesn't have a very clear physical interpretation, but mathematically you can still use the thing. So that's called an affine parameter. So you can replace this tau via some elementary mathematical transformation into one thing that still describes where it is. It's just not time anymore. So. Let's do the exercise. In the lecture we already said that if you have a Minkowski spacetime, a real Minkowski, not locally but a globally Minkowski spacetime, then all your Christoffels are going to be 0, right?
Mhm.
Because your metric tensor is well, -111 or something like that, just constants, and their derivative is going to be 0. So it's going to be 0. Just means things move in a straight line with constant velocity. No surprise there. The exercise that I'd like to do with you is suppose that we are still in a Minkowski spacetime. It's just our coordinates are not Euclidean. It's not x, y, z, and t, but it's going to be t, r, theta, phi. Still on curved spacetime. It's just crappy coordinates. Or they're fine coordinates. It's just
Flat space-time.
It's still flat. Well, let's be puristic here. By flat, people typically mean Euclidean flat, but now we have time as well, so we would call it Minkowski flat or
Minkowski.
something like that, but sure. Do you remember we derived the expression for flat space-time? You see, I'm doing it myself now. For Minkowski space-time, but in spherical coordinates. We derived the expression last week. Maybe you remember it, maybe you have it somewhere.
It's r squared sine theta. No, it was r squared in the first.
You sure?
Oh,
How many
Because if we are on the
It was
surface of the sphere, we're not.
Oh, yeah, true.
So you're talking 4x4.
Yes, we need 4x4, so
Yeah.
these are coordinates.
So -1, 1 on the diagonal, and then r squared sine.
Ah, yeah.
Sine squared, right?
Yes.
Yes, we derived this ourselves. Well, not the -1 part. We derived this part because we're only talking about space with them. When you said that, when you mentioned just a second ago that this one was 1, I think, or something like that, but if you're on the surface of a sphere, an actual curved two-dimensional surface, then this part would not have been there. Because on the surface of a sphere, you don't have any r direction to move in. You can only move in theta and phi direction.
Okay, so this is 4-dimensional space-time in spherical coordinates.
Yes, it's
Minkowski
4-dimensional
space-time.
Minkowski space-time in
Yes.
spherical coordinates. So this is a completely flat space-time. It's just that the coordinates don't make it appear as such. Now, because we derived this expression ourselves, we know that it's secretly just Minkowski space-time. But if we had not done that exercise and I would just given you this metric tensor, you might not have picked up that it's really just Minkowski space-time. But we know that it is. So, by the way, that also means that we know exactly how things will move in this curved space, or this space-time, right? Straight line, constant velocity. So it's a nice check whether our methodology will work. Let's write down the Christoffel symbols. Let's write down the G-desk equations. and check whether a solution to it is a straight line. It should be, because it's really just Minkowski, so things should be moving in a straight line. So let's write down the equations, the geodesic equations, these ones, there are 4 of them. Let's check whether the solution is indeed a straight line. That's the plan. How many equations do we have, by the way? Not this equation, but it's a system. How many of equations are in there?
4.
4. One for time, so you know how time is going to depend on tau. 1 for r, 1 for theta, 1 for phi. We discussed this in the lecture a couple of days ago. This itself is 16 terms. So yeah, life sucks, right? So don't blame me, don't blame gravity for this. Blame the weak equivalence principle. Blame the fact that particles do not have a preferred coordinate system with which they want to get to rest. That is the cause of all of our trouble right now. Okay, well, we have no choice but to go through all of them. Let's start with the
0, 0.
yeah, I was looking for news. So we have 4 of them. We have time, r, theta, phi. So I'm happy with either. So we have to do them all, so might as well start with one. So any preference? Any favorite coordinate?
Theta.
Theta, sure. Okay. Let's do theta. Alright. Well, for us to write down this equation, we're going to need the corresponding Christoffels. Man, that sucks. Because if you fix this view to be theta, then, well, there's still 2 indices and each can have 4 values, so there's 16 permutations. So there might be 16 different Christoffel symbols for just the theta. Now there's a dumb way of doing this, and that is take all alpha beta permutations and calculate it for each.
Maybe you can
16.
eliminate some terms.
Sorry?
You can eliminate some terms.
Yeah, of course. That's exactly a clever way to do it. You can already tell, well, this is going to be 0, that's going to be 0. You can usually immediately tell which of the Christoffels are non-zero. And we're only interested in the non-zero ones, right? The 0 ones will make you add 0 contribution. So let's write down the Christoffel with mu is theta. U don't want me to write this down during this public lecture, that I understand.
Isn't the metric tensor in the Christoffel symbol formula actually the inverse metric tensor of that one?
Yes, you need this
Because
one.
it's a contravariant
Yes,
expression.
that is very good. That is of course the next point. That this thing here looks like a metric tensor, but it isn't. Metric tensor has the indices down. It's double covariant. And what you need here is a double contravariant version of the metric tensor. Well, you know how to calculate contravariant versions, right? You know how to get indices from upstairs to downstairs. If you want to get this one up, so if you want to get the mu up, you have to contract it with the metric tensor itself. So just to show you that it might become a difficult problem, if you want to have this with one index raised, you get that from taking the lower index.
Oh, you use the same metric tensor. You don't use the Minkowski metric tensor.
No, you use the same metric tensor.
Okay.
So if you want to raise or lower indices in a curved space-time, you have to use its metric tensor. So you see that this becomes a difficult problem, because to get this index up, right, it's down here, but you want to get it up, you have to contract it with exactly the thing that you're looking for. And you have to do it twice, because the nu also has to go up. Nu theta. So you know this one, and you have to find the expression for this one, but it appears in itself
Use
twice.
it twice.
Yes. So this can, in practice, be a difficult problem. But it's a solvable problem, but it's just recursive. The thing is defined in terms of itself. So it's a difficult problem, but it's a solvable problem. And you're right, and unfortunately we do need that one. Here's good news. If your metric tensor happens to be diagonal, then this one, you don't have to worry about this. It's just this one. That's a mathematical statement. Feel free somewhere in your lazy Sunday afternoon to do this for yourself.
That just means if you invert each element.
Yes. Well, except for the zeros, but the
Yeah.
non-zero ones, yes.
That's easy.
So yeah, that's easy, right? So you might want to prove this for yourself, that you assume the metric tensor to be diagonal.
Yeah, I had to do that to get
Oh, you
the
did?
correct. I had to do that.
Okay, did you manage?
I didn't know it worked that way, but I don't know, I assumed
Okay.
it was like that.
It's a good assumption. So, fortunately, it's going to be extremely rainy this weekend. So, we have lots of time to work on this. Now, you can prove this, it's not that hard. But generally speaking, you would have more trouble doing this. Now, a follow-up question, of course, is are all of our metric tensors going to be diagonal, please? And the answer is yes. The ones that we're going to work with in the next few weeks are all going to be diagonal. Another good question for the other group was, okay, but since you can change the form of the metric tensor by using different coordinates, same curvature, just different coordinates, just as we did here, we went from -1, 1, 1, 1 to -1, 1, something, something. Apparently you can change the form of your metric tensor by using new coordinates, yes? And the question that I got was, is it maybe possible if you have a non-diagonal metric tensor to choose coordinates such that it becomes diagonal? If that's the case, then you never have to worry about this. You have postponed the problem because you have to find the right coordinate transformation that makes it diagonal, but you can maybe rephrase the question. And the answer is I don't know. I don't know. If, my gut feeling says no. I feel that there's curved spacetimes that cannot be written as diagonal metric tensors. But this is gut feeling. I don't have a formal proof for this at hand. Something to think about during the next Sunday rainy afternoon. Okay, but here life is easy. Okay, I need suggestions. We're looking for the Christoffels with theta upstairs. All the non-zero ones.
G theta nu would only have values where nu equals theta.
Yes.
Yeah, exactly.
That is perfect, yes. This is of course the kind of smart looking that we can use here. The fact that it is diagonal means that, oh excuse me, this one here, yes.
Yeah.
The fact that this one is diagonal, using this trick, means that nu, this contraction, will give zeros except when nu itself is theta. So that solves an enormous amount more issues. One of the contractions just says, well, replace all nu's by thetas. Good. Well, that makes life easier, yes? One contraction is gone. So thank you for that suggestion. Works beautifully. Any more follow-up suggestions here? Maybe we could tell.
The same is true for beta and alpha.
Yes. Because this thing is diagonal, that means that the only term where this metric tensor element is going to be non-zero is when theta is beta. So again, the diagonality argument. So the only way that this is non-zero is when beta is theta.
And alpha, right?
Why?
For the second.
Second.
Oh yeah, sure. In the second term, alpha has to be theta. Agreed. For the same reasoning, yes.
So does that mean all the alphas and betas are thetas in that expression?
Yes.
Yeah.
And the last one is
Yeah.
Are you only changing the values in those terms,
Oh, in those terms, yes.
not in all of them?
No. The contraction runs per term.
But alpha has to be phi, right? In the first derivative. If alpha is not phi, then you will get 0 in that term.
If alpha is phi, you will get 0. Because what you're requesting is make alpha phi,
Ah,
that means
true,
take a phi
true.
derivative, but
Yeah,
nothing
yeah.
depends on phi.
Mm.
So alpha is certainly not phi.
So in the last term, it's still G alpha beta.
Yes. Yes, I mean the betas and the alphas that I write down are valid per term. Hey, speaking of per term, how about this one? Yeah, you were about to say something.
Yeah, I'm thinking about like derivating. So that means that you're derivating the component in respect of theta.
Yes.
So that means that it has to be phi. So that's the only one that has
Exactly.
theta.
Exactly. So here a theta derivative is taken, but you can only take the theta derivative of this one, the phi component. So in this term, alpha and beta can only be phi. That's the only non-zero possibility there.
So because of the metric tensor itself?
Yes, because the metric tensor tells you that only this one is theta dependent. So only this one will have a
Because it
derivative.
has the R squared.
Sorry?
Oh wait, no, never mind, I get it.
Okay. Oh, now, okay, so this one is completely fixed, right? We know the only possibility for the last term to be non-zero is when alpha and beta is phi. Good. Now, let's go to these terms here. If we do make beta theta, as we have seen that you can only do this. Can you say something about alpha?
0.
Alpha 0?
Sorry, no. 5, no, 5. No.
Let's point what g theta theta is in our metric tensor. Which of the numbers is that?
R squared?
R squared.
Yeah. So it should be with respect to R.
Yes. So the theta theta that we've seen is the only one that is non-zero, is itself r squared. So the only derivative that you can take is when you take the r derivative. So alpha must be r in this one. That's the only non-zero possibility there. So we're really doing two things. We first checked when the metric tensor element itself is non-zero. That gave us beta is theta. And as a next step, we checked whether its derivative is 0. That gave us alpha is r.
So beta must be R too. Oh
Yes.
no, yeah.
By the same reasoning, in this term, this should be true. And I think by now we have exhausted all possibilities. This is the only Christoffels you can
Yeah.
construct. that
For
are
the last
non-zero.
term, it could be phi or R.
This one?
Oh no, those are already defined. Never mind.
Yes.
Yeah.
Yeah, I mean, you have to take the theta derivative.
Yeah.
The only theta derivative you can take is
It's the phi,
phi.
yeah.
And so there you go. So that means we have of all these possibilities that you in principle could have, we have done the clever way. We haven't calculated all possible probabilities alpha and beta and hopefully got something out. No, we just look carefully at our metric tensor. We saw. So we have seen now that the only non-zero ones are alpha beta. When alpha is r or beta is theta, this is non-zero. The other possibility we've seen is this one. And the final possibility that you have is that one. Those are the only three that are non-zero.
Wait, how did you get that from? Oh, by replacing alpha and beta with
I
phi.
just take to the alpha betas and I can read off which ones are non-zero because we listed them there.
I also read that the lower indices might be symmetric.
They don't might be.
They are, right?
Yes, if you would swap alpha and beta, just forget about this particular example, just a general definition, well here it is. If you swap alpha and beta, you swap alpha and beta here, you also swap them here, you also swap them there, you'll get exactly the same expression.
Okay.
That's good, because alpha and beta, if you didn't know about that, you would think that alpha and beta gives you 16 possibilities, but the swapped versions is just the same. So that gives you a total of 10 possibilities. So it's not quite as bad as it looks. The symmetry of the lower indices.
Wait, 8, not 10, right?
No, no. If I would write all possibilities, all 16 possibilities, you would guess the fact that you have 16 permutations. But you know that alpha and beta can be swapped. That means that everything here, the swapped version is just this, right? Like this is your row, and this is your column. Then swapping row and column just means that you go from here to there in a matrix. So that means if you have
So that
these
makes
numbers,
no difference.
then you also have to have these numbers.
Mm-hmm.
Now let's count. 1, 2, 3, 4, 5, 6, and then there's a diagonal 7, 8, 9, 10 possibilities.
Oh, okay, yeah.
So the symmetry of the lower indices means you have 10 possibilities maximum. By the way, do you still already see that here is one of these versions? Swap lower indices.
Yeah.
So we don't have to calculate both of them, right? You calculate one of them, you know the other one.
And that's
But this-
always the case for
Always.
a diagonal tensor.
No, for any,
Even for a non-diagonal
even for
tensor.
non-diagonal. This is always
Why?
true. You can see immediately from the general expression. Swap alpha by beta, you will see that you get the
You
same
get the same.
result.
Oh, okay.
Okay, we-
This is what it was done for the mu equals theta.
Yes,
We still have to do that 3 more times.
yes. But we can be a little bit more quick because we now see how you do this quickly, right?
Sure.
But yes, so when I was a student and I was learning general relativity, I found this trick. I also found a trick of my own that I was very proud of. And then at some point I just decided to program it in, so I just wrote a mathematical script that calculates all possible tensors given a metric tensor.
Wow.
It's very handy. I still use it to this day. That program is 16 years old. It's programming. It's not like it's a huge complicated thing. But I just press a button, brrr, I get all my metric tensors and my Christoffels and all other tensors that you. It's very easy. All right. So we have this statement that this swapping of indices will give you the same is true for all metric tensors, even non-diagonal ones. Now let's calculate what it is. I need your help for this. We need to see whether you get the right expressions.
Half r squared sine squared theta.
One more time, I forgot what the first part was.
R squared.
Is r squared?
Yeah.
Are you sure this is good?
Yeah, to the power of
Is
4
r
squared.
squared?
No, but you use the inverse one, so it's 1 over.
Oh. Okay, there you go. Remember, there's a difference between contravariant and covariant. It's not the same thing. Okay, well, let's go for this one.
So derivative of r of r squared.
Yes. And this one is 0 and that one is 0. I think we can manage this, right? It's not too hard. Oh, she's right, of course. I mean, there you go. That's the inverse of r squared. So 1 over r squared. The 1/2 comes from the definition, and this says take the r derivative of g theta theta, which is this thing. There you go. If I'm not mistaken, this is 1 over r. Great, good. And by the way, that means that this one is also 1 over r by the symmetry in lower indices. So please do not go through the calculation there. Copy paste it immediately. Okay, phi.
Half 1 on r squared.
Okay.
Partial derivative of theta of r squared sine squared.
Okay, so the partial derivative of this thing with respect to theta.
Yeah.
This guy's derivative with respect to theta, the r squared remains. This thing sine squared derivative with respect to theta is sine theta cosine theta.
2 sine theta.
You're right, yes, thank you. Yes, you're right.
And there's a minus somewhere as well,
Is there a minus?
from the formula.
Oh yeah.
Or did you?
Oh, yes. Yeah, that's true too. I mean, this one comes with its own little minus. Yeah, that's right. Okay, well, a couple of things drop out. I see some 2's dropping out, I see some r squares dropping out. I find minus sine theta cosine theta. Great. We now have all Christoffels for the theta direction. Still 3 more to go. Is all clear, yeah? No mysteries here.
Sorry, you're only doing, like for each Christoffel symbol, you're only doing like one of the terms only because the alpha and beta are per term.
Yes.
So if you substitute those alphas and betas in the indices
Yes.
across the others, they're just going to give you 0.
Yes. We've seen that this one can only be non-zero if alpha is theta and beta is r. So if I'm going to take this guy's beta and r, then it's going to be 0.
Okay.
When you later substitute the Christoffel symbols into the geodesic equation,
I know where this is going. Good question.
because now we just have values. We don't have anything that's specific to different indices, or that can be contracted with dx alpha by d tau. So how do you substitute it, or will we get there? I'm sure we'll get there.
We will get there.
Okay.
We will see it.
I think you should.
In fact, let's do it right now. Let's write down the corresponding geodesic equation for theta. So let's make a little box here where we're going to write the resulting geodesic equations. Somebody really wanted to start with the theta geodesic equation. Okay. I've written down the first term for you. That's the easy one. You tell me what the other ones are. Right. I was kind enough to write down this one for you. And you tell me what the rest is.
Let's take the first one. So
Okay.
theta. Yeah.
Okay. Now what?
Ali.
Now it's when alpha equals r and beta equals theta.
Yes.
So we need dx r by d tau, dx theta by d tau.
I agree.
So the Christoffel symbol is a you multiply it by that value, and
Well, you contract.
with the with the corresponding indices on
Yes.
the
Yes,
derivative.
that's what a contraction tells you.
Yeah.
This alpha has to be that alpha. So that the only alpha that works is here when all alphas are. So this necessarily must be r. That's what I wrote down here. The other one must necessarily be be theta. So that's what I wrote down.
Why are you running it as r, not x?
No, I could. I mean, we will mean something like this, right?
Yes.
But it's just notation-wise.
It's nicer to have a definitive, like once you decide what your coordinate is.
Yeah,
it's
I mean,
nice.
this xr part, might as well call it r.
Because when I see an x with an index, I always think that index could be multiple things.
Yes. Okay.
But if you want, feel free to write down x theta. We mean the same thing, it's just notation. We're not done yet though.
Equals 0.
No, aside from that.
Oh no, we need to add all the other ones.
Yeah, I mean, we have some more Christoffel, so the
Yes.
contraction consists of more non-zero terms.
So there's only one geodesic equation for each coordinate.
Yes.
Okay.
But how many terms depends on how many Christoffels are zero
Yes.
or non-zero.
And the next one would be the same, right?
Yes. In fact, it will be exactly the same.
So you can just multiply that one by 2.
Yes. The Christoffel is the same. And you have to multiply it with this product of two derivatives, but the derivatives are the same as well, right? So you can just put the 2 here. Good. Okay, so we've taken care of that one and that one. Good. Still not done yet.
So the last one is minus sine theta cos theta.
Okay.
And then it's a double derivative
Careful.
of phi, no? Or is it not?
It's a single derivative squared.
Squared, okay.
Yes, it's not two derivatives with respect to.
Okay.
Yeah, it's a product of these two.
Equal to 0.
That is equal to 0. Okay, there we go. So here is the differential equation for how theta moves according to general relativity in a Minkowski spacetime, if you were unlucky enough to write it in polar or in spherical coordinates.
Shouldn't be 0 though?
Too beautiful.
It is right.
How the fuck
No,
do you
because
solve that?
shouldn't come that they gamma becomes 0. Like
No, only in why would you think that the gamma and the Christoffel symbol is 0?
oh, because like since we're not like in Minkowski space,
Yes.
shouldn't it like and then have to be 0 in the end?
Why would it?
I mean, just we're in Minkowski space, shouldn't it?
In a Minkowski space, things move in a straight line.
Yes,
Yes.
shouldn't be like 0. So
No. I'm teasing you a little bit. I of course know the root of your question. Let's take this room here as a Minkowski frame, yes? And let's make this our x coordinate, this is our y coordinate, and there's time, our watches and such. We know that in this Minkowski frame, things will move in a straight line, constant velocity. I'm going to ignore gravity for that reason. So my phone is fine, so constant velocity. In its x direction, it will have a straight line and a constant velocity. Also, it is y. Right? The y happens to be 0. So there you go. The y is not 0, but it's some fixed number. Okay. Now, so that is your straight line. That is correct. But you can also describe the flying of this thing in terms of polar coordinates. Now, polar coordinates means here's your origin. here's my phone. This is the theta, and this is the r. But the thing is moving in that direction. That means as the thing is moving that way, the corresponding r has to, theta has to adapt as a function of time.
Oh,
Yeah.
okay.
Non-linearly.
Oh, so that's why it's like this.
Yes, this is
Okay.
why it looks like this.
Okay.
So it's still a straight line, it's just it doesn't represent itself very well in the way that it looks.
Okay.
I promise you that if you solve that equation, well, you have to solve the other ones as well, but the resulting theta as a function of tau and the resulting r as a function of tau, ask a computer to draw this for you, it will simply just give you a straight line. It's just, we happen to have chosen spherical coordinates which makes it difficult to represent a straight line, but it is in there. Yeah, so we have the theta coordinate now. You know what the crappy thing is? We discussed this on Tuesday. If you want to solve for theta, you need to know how r looks as a function of tau, and how phi looks as a function of tau. So it means we also have to solve the phi differential equation and the r differential equation. So it means we have at least 2 more geodesic equations to write down. Right. I mean, I cannot solve this if you don't tell me how theta depends on tau. I do not know what this thing is. I cannot solve this equation. And how do I get theta as a function of tau? Well, solve its. Oh, well, actually, theta as a function of tau is this one. Excuse me, r as a function of tau. I need to know r as a function of tau in order to know what this is, and only then can I attempt to solve this differential equation. So,
Well, doing it for some of the other variables, maybe eliminate some of those terms.
one hopes. It will be very good if you.
Like isolate one of the derivatives so you know what it is
Fully
and you can put it
understand.
in.
And sometimes that works actually.
Yeah.
That if you would write down the other geodesic equations, that possibly you can eliminate one of the unknowns in terms of the things that you do know. You,
Yeah.
you decouple your system of differential equations. That happens on occasion, but it's
Not
unfortunately
always.
not always. Oh, man. Sucks to be us. Now you know our strategy, right? Now if only we had stuck to Euclidean coordinates, then life would have been much easier. But it's a good exercise. It's a good practice in writing down these things and how to solve them. You know our strategy. We're also going to write down the phi and the r. Hopefully the phi and the r itself do not depend on t, because then we also have to drag the t differential equation. You get 4 equations to solve. But the strategy is if we have our equations, what you usually would do, if you didn't know any better, is try to solve these. Our job, we're going to do something more simple. We already know that the answer is going to be a straight line. So what we're going to do, we're going to have our system postulate or it has as a trial solution the straight line, put that in and see if it solves it. Right? It's the difference between solving the differential equation and somebody's giving you a solution and you checking whether it's true. So we're going to do the checking part.
We're doing the polar coordinates just like as practice. Because
As practice.
if it were just Euclidean, it would just be 1, 1, 1, 1. And
Yes,
everything
and
would just drop out.
yes, you would have that in Euclidean coordinates. It would just mean that those 4 coordinates, its second derivative would all be 0, which is the same thing as saying that an x, y, z, they move with constant velocities. You would have got to your straight line immediately. So there's a good lesson here. Make sure you choose your coordinates right. You can save yourself a lot of time, effort, and trouble. Do you feel like having a break before we continue with this exercise?
Definitely.
Yeah. But in principle, you see how this is done, yeah? There's no, might be difficult in practice, but there's no principal difficulty in the strategy. That will work. Okay, good.
Yeah,
So, have people in the meantime been able to figure out the other ones?
We were
We were
resting.
supposed, yeah, exactly. We were supposed to.
Well, we can do this much more quick now, I think.
Yeah.
So, let's go for the, well, we need to find the r at the very least, according to that equation. So let's,
is equal to r.
sorry?
So let's do for r.
For r?
Yeah.
Okay. Let's go with the r version. Well, by the same argument as before, if you recall, there's an r nu here. This is nu in the original equation, this is nu, and this is nu. But yeah, it's this contraction over nu is over a diagonal inverse tensor. by the sheer good luck of us having a diagonal matrix, diagonal metric tensor, this you all have to be R. Okay. Now, let's do the same exercise again. Let's see, let's write it down in red under each term, which of them are going to be non-zero given that this is R, this is R. In fact, let me be immediately quick about this. This is always going to be 0. You see why, right?
Because the tensor component at RR is constant.
Yes. So the only beta that will make it survive by the diagonality of the metric tensor must be beta is R. But the RR one is 1, and
Yeah.
its derivative with respect to whatever is going to be 0. So that part is 0.
And that's the same for the second.
Same here, of course, absolutely. Now, that makes life very easy here. Okay, and this one here says, okay, now you have to take a derivative with respect to R of some metric tensor elements.
Either theta, theta, or phi, phi.
Yes, both of them will work, both of them will give something different. But we will get -1 R. And yeah, of course, this is completely true. You have to take R derivatives, so it's either this one or that one. Those are the only ones that you can take derivatives of. So, life is very simple. We can do this a lot faster now that we've had some practice. The only ones that survive are when alpha and beta are either both phi or theta. And all other metric tensors with the R upstairs are all 0. Let's write down immediately what they are. What is GRR?
1.
That is 1. Well, it's 1 over 1 if you would be fuzzy about this, but yes, that's 1. And then we have to take the derivative for this one of G theta theta.
2 or sine squared theta.
-2.
No, it's theta
Minus-
theta. So
Oh,
we're
the
taking this
theta one,
derivative.
yeah.
So this
2.
R will cancel that
Oh,
one.
you put the minus.
So if I'm not mistaken, this is minus R.
Mhm.
Okay. The phi phi.
So R square is sine theta cos theta.
This will give you minus R sine theta cos theta. That's what you said, right?
Yep.
So it's this.
Yep.
No, I'm actually stupidly mistaken here.
No.
No, you only take the derivative with respect to this R and not the sine
So it's
theta.
2R sine squared.
Ah, yeah, true.
Yes. Yeah, and the 2 drops against this one,
Mhm.
and the
The minuses should cancel.
there's no
Oh no,
cancelling
there's
of minuses.
there's only one minus, yeah.
So I think this is it. Great. We now have our second geodesic equation.
Why does the R cancel over there?
There's no cancelling of R. This is an R.
Oh, that
Is
looks like a 2.
Yeah. Sorry, no, that's an R.
Is that sine theta squared or sine squared theta?
Yeah, I'm just being very stupid here with my T's and my R's and I did my signs, but I think this is correct.
Just sine R theta.
Sine R theta, yeah. It's the R derivative of theta, yes. Or the sine theta to the power R. That will be a crappy geodesic equation to solve.
Yeah.
Okay, so let's write down the corresponding geodesic equation. This is the R differential equation. Now, I am kind enough to write down the first term for you.
Thank you so much.
You're so welcome.
So it's gonna be minus R the theta by the tau squared.
That is correct. This is tau. Anything else?
Minus R sine squared theta d phi d tau squared.
And of course, note here, there you go. This factor of 2 that we had previously, we don't have now. We had this factor 2 here that was because of the lower indices that you could swap around. You won't have that here. I mean, you can still swap them around. How to put this more, how to put this a little bit better.
They
We
don't
do
give
this
a
com-
new part of the tensor, is that what you mean?
Sorry?
They don't give a new part of the tensor.
Yeah, that's what I was looking for. At the moment that you have two separate indices and they're different, there's two of those locations that get the same contribution. But if they're the same, you're on the diagonal, there's only one. So this is why this one does not come with, this one doesn't come with an extra 2.
Oh, never mind.
Okay, so we have the R differential equation now. Good. Fortunately, there's no t derivatives in there, so there's no need at this point to also introduce the geodesic equation for the time. Final one to go. Again, we can be quick, I think. Let's go with the phi's. Let's skip a couple of steps immediately. The diagonality of the inverse metric tensor will say that if the mu is phi, then the nu is phi. That means that all the mu's here are phi's. I see one term immediately always being 0.
The last one, because there's nothing that depends on phi.
Yes. None of the terms will depend on phi, so the derivative of straight phi will be 0 always. Good. Anything else?
And so for the first one, you have beta has to be equal to phi, and alpha can be equal to r or theta.
Yes, exactly. That's entirely correct. The diagonality of the metric tensor says, well, if this one is phi, then this one must be phi, otherwise the metric tensor itself is 0. Now, so we're now looking at this metric tensor element, and you can take two types of derivatives, either the r derivative or the theta derivative. And this term will lead to the same conclusion. So, the only options that we have, so in red again, is that beta is phi, and then alpha must either be theta or r. And in this one, will be this. Those are the only options. You know, life is so easy when metric tensors happen to be diagonal. Okay, good. That means the only Christoffels that we have here.
So you have 4 options.
Do we?
Oh no, because you switch alpha and beta.
Yeah, so
You have 2 options.
yeah, I mean, this one and that one will give you the same contribution. So there's really only 2 real options here. So let's go with this one. When beta is phi, then alpha is either theta. This is this correct? Yeah, this is correct. Or it's r. Those are the only options. Let's write down what they are. Can somebody tell me some outcome here for this combination? Wow. Here we go.
1 over r squared sine squared theta.
Yes.
D theta G left.
Indeed, don't forget that it's the inverse. So there's that. And then we have to take the, here's a phi has to take its
The theta derivative.
Yes. So the theta derivative of this thing is what we need.
That's 2r squared.
So it's not 2r squared. The r squared is a constant as far as the theta is concerned.
It's the derivative of the cotangent squared. Because it's 1 over sine.
Yeah, but you're not taking this guy's derivative. You're taking this guy's derivative.
Oh right, it's not the inverse. Yeah, you just multiply by that one.
Oh, so isn't it 2
Then it's 2.
But the r squared doesn't feel the derivative.
Yeah.
Okay,
Yeah, but the 2
Then
comes
it's
from
2
the
sine
power.
theta cos theta.
I agree. So this guy's derivative is sine theta cosine theta with a 2. This is correct, I think.
Yes.
That's it.
Thanks.
Then, if I'm not mistaken, this will give you cosine theta over sine theta. Yes.
So cotangent.
Yeah, yeah, that's true. Yeah. No, you're right. I never think in terms of cotangents, but you're right. Good. One Christoffel done. Last one to go.
If the last one is half times 1 over r squared sine squared theta times the derivative of r squared sine squared theta, but in respect to r, which is
2r sine
Yes.
squared theta.
I didn't use that part.
That will be this. One over r. Great. We can now write down the phi geodesic equation. It's good practice in doing our contractions. You tell me. Again, the kindness continues. The first thing of mine.
So
Cotangent delta phi delta tau delta theta delta tau.
put it down.
Like this.
Yeah,
Okay.
and I think it's actually 2 because because it's symmetrical.
Yes, exactly. Thank you. You might have just left open some space there. That was for the two. Okay. Anything else?
Plus 1 over r, or 2 over r, of dr d tau and d phi d tau.
There you go. Well, took us some work, but there you go. These are our geodesic equations.
You multiply them by 2 because you would do the same thing if you switched the indices.
Yes.
I get the same one.
The
Okay.
double contraction that you
Right.
have here will have it, one of the terms will have theta phi,
Yeah.
but it will also have the phi theta.
Yeah.
And both of them give you the same contribution.
Okay.
So they give you twice that contribution.
That's a nice fact.
Yes. But notice that it only works if the two
They're different.
are different.
Yeah.
Because in a double contraction, there's only one way that you can have both indices the same way.
Yes. Yeah.
Okay, good. Now, so it's interesting to see that the geodesic equation for the time is apparently not part of this system.
Yeah.
So what does it tell us physically? Because usually, generally speaking, it would be. So maybe
the
you can already.
coordinates don't depend on time.
Sorry.
That the coordinates don't depend on time.
No, they do depend on time.
On t.
Well, if they depend on
They
tau,
depend on
they
tau,
will
yes.
also depend on t in some way, right?
Yeah.
Because t and tau are dependent on each other.
Yeah.
But that equation for t, as its solution, will have t as a function of tau. We would call that time dilation. How the proper time and your time are related to each other. That's what that t equation tells you. And apparently it's not part of how the thing moves through space. Apparently time dilation is independent of how it's moving through space. Maybe that tells you something.
So it's Minkowski space time or something?
Yeah. The opposite is certainly true. If it is Minkowski space-time and you let something move by gravity alone, so it doesn't accelerate, you can still move through Minkowski space-time with acceleration, but you have to do the pushing yourself. But if you let gravity do it, then in a Minkowski space-time you would have a constant time dilation. That is very true. I'm not sure that the opposite is true. If you're constant time dilation, therefore you are in a Minkowski space-time. The arrow certainly works one way, not the other. So yeah, the question is one of physics. The fact that the way that time dilation works, dt d tau, that is not part of apparently our spatial motion. Well, there's physics there, right? I mean, why doesn't it? Maybe it tells you something about the kind of motion that it has to go through.
Sorry, why is it not appearing? This might be like a dumb question to ask, but
Why is it not appearing?
why is the T term like not in there?
Well, that's what Christoffel symbols tell us apparently. So nature chooses apparently to let things move through space-time in such a way that the spatial motion does not depend on the time dilation. That's not answering your question, I'm just rephrasing it in physical terms. Why doesn't the t appear in these spatial geodesic equations? Well, apparently nature doesn't want time dilation in there.
We're gonna see always the same time dilation
Yes.
from the other.
Yes. So that means throughout the motion of the things through space, these three equations, the time dilation apparently is going to be the same. Now, time dilation, you might remember that that's a gamma. You might remember there's a v in the gamma. If the time dilation apparently is going to be the same everywhere, what does it say about your v's?
It's constant.
Yes, so you can tell that something to do with the constant velocity here. It's a roundabout way of saying it, but it's in there.
Mathematically, as in, like, if you put t in the Christoffel, it's going to give you all zeros.
As in, if we would take the
Yes.
calculator, yeah, I'm guessing that that's going to be the case, yes. Yeah, it should, because otherwise, yeah, I think it should even, yes. Now, is that the same as saying, oh, therefore, because time dilation is constant, therefore it moves with constant velocity? That is not, that's not entirely necessary. What is a fact from this is that you can immediately tell the time dilation, whatever it is going to be constant. That does not necessarily mean that the thing moves with constant velocity. Because in general, you have two time dilations. You have due to gravity and you have due to its motion.
But that means also that the proper velocity is zero, right? Because if t is constant.
No. T is not constant. It moves, but it moves at
The
fixed rate.
same, yeah.
Yes.
Okay.
So you have gravitational time dilation. Right? Your presence due close to mass will slow down your time, and you have special relativistic time dilation. If you move fast, your time will slow down. And I guess you can find a situation where your gravitational time dilation and your normal high speed velocity time dilation sort of balance each other out. That none of them each is fixed, but they have a fixed total amount. So you're allowed to accelerate and go slower. So you're allowed to change your special relativistic time dilation, but your gravitational time dilation will compensate for what you're missing. I'm sure that there are situations that you would have that. So it's tempting to think there's a constant time dilation. There is, and therefore constant velocity. That step is not necessarily true.
So this is what it's saying is about the total dilation.
Yes, because it's a total dt d tau. Now, we are used from special relativity that the only way that dt d tau can be different is due to your relative motion.
Yes.
But gravity will also throw in a little bit. So just the fact that dt d tau is a constant is some combination of gravity and relative motion. So concluding that therefore your relative motion must be constant is not true. You can have a non-constant relative motion, and whatever then messes up your time dilation is compensated by the gravitational time dilation. I'm sure you can come up with that
This is where the
situation.
Minkowski line
We don't know.
Okay, we
Supposing
don't
you
know
don't know that, okay?
but
No,
you
you're
know
right.
that there's no gravitational time dilation.
No, of course. In our case, where we started with a Minkowski spacetime, we know that there's no gravitational time dilation. So, given that, yes. But if I give you this and you had not known before, and that it was secretly just Minkowski spacetime in spherical coordinates, then that conclusion would be too preliminary. So, now you can solve this set of equations. Very difficult. Look, the theta that you have to solve for appears in this guy's equation as a cotangent. So you're looking for some theta as a function of tau in such a way that if you take its cotangent and take a couple of derivatives and how r moves, that's yeah, that's
or
hard.
in a computer.
Yeah, you can ask some numerical program to maybe and then find that it's just a straight line. Now, the strategy that we promised before we started this exercise was, you know what? Let's just pretend that we were smart enough to think this might be just a spin Minkowski spacetime. Let's just check a solution instead of trying to derive a solution. So if it is a Minkowski space-time, if that is our guess, then at the very least we should have a straight line with constant velocity as a solution. Agreed? So let's assume that the solution, again, it's an assumption, is given by a straight line. And by a straight line, that means some r is a function of tau, some theta is a function of tau, some phi is a function of tau. We guess this thing, put it in, see if it works, if it solves the system. So our question now is how to write a straight line motion in terms of spherical coordinates. Really, that was my flying phone with its little theta changing in time and the r also changing in time. Hard, right? But I'm sure we can do, we're a little bit smart, we can do better. So my flying phone here, if this is my x and my y, then my flying phone has a good, here's my theta. Phone flies, that means my theta has to compensate. So a straight line in terms of theta's function of tau is probably difficult to write.
Could do it in XY and then we know how r theta and phi.
Yeah, sure, we could, absolutely. We could
We
just
can
say,
also
you know,
move in XY coordinates, right?
sorry?
So instead of the z, so we can remove one of the angles. Can we do
That
that?
would be also an option, yes. So hers is, let's take my flying phone and calculate, knowing that it goes, or assuming that it goes with constant velocity, and calculate by sines and cosines how the theta goes as a function of time. That certainly works. Suzanne, I think that your option was,
No, just move in the XY so that we don't have the other angle.
yeah, how about this? It flies in this direction, yes? You know what? Just rotate our x-coordinates such that it flies along the x-coordinate, or the r-coordinate, I may should say. You see, the nice thing, here's a rephrasing of exactly the same point. Instead of throwing it in this direction, why don't we throw the thing in exactly along the r direction? If it's a Minkowski space-time, shouldn't matter, right? Every straight line should be a straight line. Doesn't matter in which direction you throw it. Might as well throw it along the r direction. You don't have to. You can also do your trick, and it's certainly more general. But as a quick check, let's just throw it along the r direction. And the spherical symmetry of the Minkowski spacetime says it doesn't matter which one you choose, might as well choose that one. Now, so let's do that one. Let's take that option. What does it tell you about theta as a function of time? It is some constant. So we are defining a straight line now. Phi is a function of time.
So constant.
Also constant. R is a function of time.
Constant times t or something.
Well, yeah. Well, actually, we don't. Well, we would assume that it's a constant times t. Well, let's do that. Let's constant times t. Should
V
name the
deta.
constant.
V
V.
deta.
Yeah, sure. Well, I just call it tau. I know, or plus initial r or something like that. Whatever. Now a v might give you the impression that it's just a Newtonian v, namely r divided by t. But you can tell by units that this must be r, well not by units, but by consistency that it must be r as a function of distance divided by d tau. So if you really, it will probably be this.
Wait, so this is like the R that we observed it from an inertial frame in terms of like the proper time of its
Yes,
frame.
exactly. Yes. By the way, it doesn't matter for our solving. You can also you can call this whatever you want. But a guess would be time, constant times time. So this is going to be our guess. We've thrown a thing along the r direction now, just for the sake of mathematical simplicity.
Did you square the? What happened to the v?
I replace it by u,
Ah, you.
but it's the u in r direction. So it's not
Oh,
correctly writing.
r.
It's not a 2, it's an r.
And it's not an exponent. It's a.
No. It just means velocity, proper velocity in r direction. Now, if this is a solution, this is our assumption that it is, because we are smart enough to think that this is a secretly Minkowski spacetime, then this should be a solution. And if it is a solution, it should solve these equations. Let's see if they do.
Well, dr by d tau would just be u.
Sure. Okay, so let's do it here. Dr by d, where's the thing? This one? That will be
dr by d tau.
That would be UR.
Yeah.
She's putting in this thing, taking 0 with respect to tau. Sure, it gives you that. I'm sure there's more place where this happens. there's
Yeah,
not.
there.
Doesn't everything go to 0?
All
Yeah,
the
both
d
the
phi
phi
by
and
d
the
tau
theta secondary
becomes
derivatives.
0.
Yeah, this is 0, right?
Yeah.
This is 0. You know what? This is 0.
Oh, there's no way the r is isolated.
Yes, it's just the second equation, the first term. Where
Yeah.
Second equation, first term.
d2r by d tau squared. Everything else drops to 0.
Mhm.
Yes. In fact, this is 0 too. Yeah, yeah. By the way, so all of this. By the way, that tells you that 0 equals 0.
Wow.
No, it checks out. Yes, I mean, it's not a triviality. If for some reason left-hand side would not have been 0, then we would have known that this is not a solution. It checks out. The first equation is solved by this assumption. Good. And I'm sure this one, same thing. Because this is 0. This is 0. This is 0 even more. Called super 0. 0 times 0, and that is 0. So this one also checks out. Of the remaining equation, this one drops out, that one drops out. And we end up with, in order for our proposed solution to be a real solution, this has to be true. Is it true for our solution?
Yes.
Yes. Because this is a constant, taking two derivatives will make it 0. We have now found that this space-time in these coordinates allows for a straight line with constant velocity, Newton's first law. Wait a minute, Newton's first law? That sounds like a Minkowski frame to me. We do this, we put that in, that was our starting point, yeah? But it's good to see that it really checks out. If only we had stuck to XYZ coordinates, would have gotten the same conclusion immediately. But yeah, this is how general relativity works. Great, cool.
Can you imagine getting a question like, get me an inventive way of proving 0 equals 0? You're like, okay.
yeah.
Let me show you.
Exactly. Hold my beer. So, officially we have 2 minutes left, or 3, or whatever it is. In all seriousness about the derivation of the geodesic equation itself by Lagrangian methods, there's one thing I would like to show you of. Certainly not the whole thing, certainly not 5 minutes of the thing, but at least one step that you might be mindful of, and it's if you allow me to show you in our dying minutes. So you know how this now is done, yes? So from next week onwards, I'm going to give you metric tensors. Next week, black holes. Week after that, gravitational waves. The week after that, the universe as a whole. Following this series of steps, you can now calculate around the black hole due to gravitational waves or in the universe how things will move.
Question?
Yes.
It's kind of irrelevant. Does general relativity predict the expansion of the universe?
Yes.
From Earth? Oh, really?
Yes. This is our final lecture. I will show you this.
Cool.
Yeah, that's pretty cool. And it's all just this. You just need the right metric tensor. But the series of steps is the same. Because to calculate Christophel's...
Is there like a universal metric tensor?
Yes.
Okay.
There is a metric tensor that describes the universe as a whole. It's called the Friedman-Robertson-Walker metric tensor.
How do we even
Universal
know
waveforms.
that? How did we get it?
Exactly.
I
The
will,
whole universe.
Okay, there is something that's called
that was
cosmological
discovered by
principle.
And
And-
Steve.
And then there's 2 hours of lecturing in between.
No,
Week 6 or the last week of our series.
Okay.
Then we'll go through it, yes. But there is a universal metric tensor.
This hard.
This hard.
Wow.
How do we know that it's the same type of curve throughout the whole universe? Or that it follows the same metric tensor?
Cosmological principle.
Okay. I'll wait. I'll be
No,
patient.
it ultimately is based on measurement. The short answer is if you look at the universe from the Earth, you will see that the amount of mass concentration is the same in every under every angle. If you look in this direction, that direction, you will see the same mass.
But we can only look so far.
That is true. So what you can certainly check on Earth is that there is an isotropy. That at any angle it looks the same. You have to look at big enough scales. But if you look in that direction, you see the sun, and over there you see a planet, and in between you see nothing. Okay. But if you look at big enough scales, then it sort of balances out. Okay. And stronger statement is if you look at the energy that arises on Earth. This is what you do by photon counting. You've seen all these cosmic microwave background pictures, right? Where you see that all throughout the universe, the photons have the same temperature, 2.73 Kelvin, with only differences of 10 to the power minus 5. So that means that the energy that arises at us from all sides of the universe is very much the same. It's about 1,000% before you see any differences. But that tells you that if the amount of the amount of energy and mass looks the same in all directions, then it means that the curvature must be the same, because it is matter and energy that makes things curve. So if you find the same amount if you see the same amount of mass and energy at any angle in space, then that means apparently the curvature at any angle of space is the same. Now, that was your question, okay? But what if you look further out, it will not be the case anymore? Here's where an assumption comes in. There's a homogeneity that if you would do the same trick, you would go to any other place in the universe and then do your sweep over all angles, you would still see that. So those are two different statements. One of them is, given one location, it looks the same in all directions.
Yeah.
The second statement is, from any point where you would have done your all direction sweep, you would still see the same.
And we assume that the universe is homogeneous, or do we know that it is?
We assume.
Okay.
The isotropy from Earth, you can measure.
Yes.
The homogeneity, you have to assume.
Yeah.
But here there's a sort of same philosophical argument, because if it's not, then apparently nature has decided that there happens to be one location in the universe where things look the same in all directions.
Yeah.
And it's either an amazing coincidence, or it looks the same everywhere, right? Now, under those two assumptions, that whatever the metric tense is, it should look the same in all directions and should be homogeneous, that is enough to find the general metric tense that describes the whole universe. And from that, you have your metric tense, and you can do these steps, and you find how the universe evolves. That will lead us to a couple of equations that we're going to work with. It's called the Friedmann equation. It tells you the expansion of the universe as a function of time, as a function of its energy contents. So anyway, that's week 6. That was a 2-minute introduction to week 6. Now, one thing I want to show you before your rainy weekend starts is the following. If you recall, let's go through the derivation of this equation. This had to be minimized. That was the whole idea. Going back to the beginning of the tutorial, we said, well, this has the exact same structure of Lagrangian physics. You would call this Lagrangian. And this would then be your function of time. And to minimize this, you just copy-paste our mathematical strategy that we derived in special relativity. Not because it's relativity and we're going to use it in relativity. No, the mathematics is just the same, regardless of context. Then this is minimized at the moment that this equation is, this is the Lagrange equation, this one here. And you have now the daunting task to take this whole square root that is now our Lagrangian, put it in here, take its derivative, then take off the result, another derivative, and set it equal to some other derivative. The result is going to be this. The step that I want to show you, it's really just an exercise in doing many derivatives, but the step I want you to show you, so you can be cautious about this, it has to do with taking this derivative that you have to do somewhere in your calculation. Okay? So let me just only take this one, just for you to see how that works. The L here is this square rooty thing. you have to take the derivative of square root. Do you know what that is?
1/2 times the square root
Okay, so
times
this
the derivative of whatever's inside it.
exactly. Yes, and then the chain rule says, and then take the derivative of what is inside. Okay, so it's 1 over the square root. I don't feel like writing out all the contents, square root, and then take the derivative of its content, and the derivative of its content would now be of no square root here. By the way, notice that when I wrote down my Euler-Lagrange equation here, I deliberately chose this index to be alpha, so as not to confuse it with this guy's mu or mu.
Yeah.
Okay. Now, here's the step that I want you to be wary about. If you're going to take this guy's derivative, well, how do you do this? I mean, well, you're going to need a product rule at least, because you have two of these things in there. Suppose that we're going to concentrate on this one. My product rule says keep this one constant and only take the derivative of this part. What is the derivative of this thing with respect to that thing? That's the part where you have to be careful. What do you think about this? Let me copy. Okay. Let me copy a little bit more.
Doesn't the index just represent numbers from 0 to 4?
Yes.
So isn't it just the same object?
Is it? Because this number is fixed, yes? We're not contracting that number. That is one of those four numbers. I don't know which one of them, but it's I call it alpha.
So it's just going to give you an element within the 4 velocity.
I agree. That's correct.
So you'd actually have 4 Euler-Lagrange equations.
Yes.
One
For
each
every alpha,
element.
you have one Euler-Lagrange equation because those are those four
Mm.
geodesic equations. So I'm now looking for the geodesic equation where I'm looking for the alpha one.
Yeah.
Okay, now, my question still remains. I have to take this derivative, this thing. Product rule says take this one constant, take this guy's derivative. With respect to u alpha. What is that thing?
That can be really different depending on what component you're
Of course.
taking.
Exactly.
At the moment that mu is not alpha, their derivative is going to be 0.
Yes.
Mm.
Except when it's alpha times 1.
Exactly. Except when mu happens to be itself this exact alpha.
Mm.
Now you have 4 terms here in your mu, yes? The contraction says there's 4 terms. One of these terms is going to be this alpha.
Yeah.
So of the 4 terms, the derivative will single out only one and will make 0 out of the other ones. So, of these 4 terms, the only term that survives this differentiation is when mu is alpha, agreed?
Yeah.
Yes.
Okay, that means that this then must also be the alpha one.
But Gideon, I agree. I see why it only picks out, especially for the space ones,
Yes.
the space components. But how, like, what if you derive it with respect to the time components?
It doesn't matter.
No.
No, it doesn't matter. What I'm writing down now holds for all the 4 components.
Okay.
You all see this step? 4 terms here, and the only one that survives the derivative is when mu is alpha.
Yeah.
But the contraction then says that this must be alpha as well.
Yeah.
Then the derivative of where now this is alpha, well, this derivative just gives you 1, right?
Yeah.
This one still remains.
Mhm.
Yeah.
There you go. There it is. This is one part of the product rule. You have to do this twice because we've
Yeah.
now checked this one. Maybe you can immediately tell me what the other one is.
Yeah.
Product rule says plus.
The
G.
same with, yeah.
Mu alpha.
Yeah.
Mu.
No, mu alpha, yeah.
Yeah, exactly.
U. Oh, right.
Mhm.
There you go.
Those are just contractions, right? So you can write
Yes.
them as their
These
covariants.
themselves are still contractions over nu.
Mhm.
Not over alpha anymore, but
Yeah.
over nu.
So they're the covariants.
Yes. Yeah, if you want, you can take these down. and
Contract
become
them,
covariants.
yeah.
But you can do something a little bit more beautiful too. You remember that the contraction index doesn't matter how you label it, right?
So those two things are the same, actually.
They are exactly the same. You might as well call this mu. You're allowed, as long as you in contraction do it for both, And you know what? The metric tensor is symmetric, so might as well swap these two around as well.
But if it's not symmetric, you cannot do that, right?
No, but metric tensors are always symmetric. They're not always diagonal, but they're always symmetric.
All of them?
Yes. Yeah, because if you think about it, the metric tensor tells you how the space and time components in your line element are related to each other. And if they're not symmetric, you're saying that one coordinate is related in the time is related to x in a different way than x would be to time.
Okay.
That wouldn't be possible.
Yep.
They should be related in exactly the same way. So the metric is symmetric.
So it's just 2 times u mu.
Yes, the two there will drop
Yeah.
out. Here's your square rooty part. There you go. So this is what I wanted to show you. You have to be careful with these things. Now, we're not going to go through the rest of the exercise. We're already over time, but we have now this one. And then the next step somewhere says take then the derivative with respect to tau. So you have to take this guy's derivative with respect to tau. That's crappy because the square root contains taus. And this, the g contains taus because the g depends on the 4 coordinates which themselves depend on tau. And this thing depends on tau. You will get a second derivative because you already have a first derivative here, and one of the terms in the product rule of the dd tau will make a second derivative. That is the part where I'm trying to write it down for you. That's this one. All the other terms you have to work out. Also have to work out the left-hand side. Squeeze everything together, and you will get this equation. But now you understand why this part is itself such a strange combination of derivatives. Yeah, it's a rainy Sunday afternoon exercise.
There are computers for these, right?
Yes.
If you want to know about price,
Einstein
you gotta
didn't
do it
have
by hand.
computers.
That's true. How did Einstein do all these things?
That was a smart.
Like,
No, but the curvature of
I don't
space
think he
time,
went
or the
out.
curvature of space was already worked out the mathematics by people before him. Yeah?
yeah.
So Gauss and Riemann and these people already worked on this. So I think he just copy pasted a lot of the mathematics from these people.
Yeah.
But yeah, somebody at some point decided that, you know what, let's write down something that's called the Udeski equation. It's quite an exercise. Okay, so tonight I will have uploaded this recording, the recording of Tuesday, the full synopsis, and I have a written version of the exactly this derivation, but I'm going to leave it to myself.
Oh, why?
Because I want you to have opportunity, the choice to work on it yourself without being tempted to look at my solution.
Okay, fair enough.
Otherwise,
It's
it's
very tempting to do this.
super tempting, but I think it's highly educational to at least have tried it once. Okay, guys, from next week onwards, application of this to actual physics, starting black holes on Tuesday.
I think at one point I decided to go from a rainy afternoon to a rainy week. To a rainy lifetime, and, you know.
Yeah, well, you're describing my life now.
Thanks, Ian.
You're welcome. Have a good weekend.